A schematic diagram of one particularly ingenious practical apparatus for optical tweezers experiments. You see on the left a laser and a device for stabilizing the direction of the beam by expanding it, passing it through pinholes. And then the beam is polarized, power monitoring. The beam sent via this mirror here, partially silvered mirror, up into an objective and focused on the specimen stage, where a polystyrene bead can become trapped at the focus of the beam. This second mirror here, also partially silvered, allows direct observation with the binocular head of a microscope and imaging with a CCD camera, also through the same objective lens. In addition, the microscope has a dichroic measurement mirror here that allows light from a mercury arc lamp to pass through to illuminate the whole sample so that the bead can be seen by the camera. But it also allows the laser light scattered from the particle to be deflected into a 4-element photodiode. So in a sense, this is a little like an AFM, and the 4-segment diode will detect the diffracted light from around the bead, and so if the bead moves in one direction, there'll be more light from that segment, and thus this quad diode can be used with calibration to read out the position of the bead directly. So let's turn to one application. There is a wonderful review, you'll find the reference in the chapter called Grabbing the Cat by the Tail, but let me just show you one example of a deduced force versus fractional extension diagram for both single-stranded and double-stranded DNA molecules. So anticipating some of what's going to come in later chapters, DNA usually forms a double helical molecule in which two molecules are paired together by the hydrogen bonding of bases in the DNA, but you can separate the two helices and end up with a much more flexible single-stranded molecule. The force versus extension diagram here is the force versus the fraction of the fully extended length of the molecule. So that's the maximum possible extension in principle. You'll notice that the extension goes higher than 1, and that's because the molecule is being stretched beyond its normal equilibrium length. To be specific on that point, we'll see in a minute that the polymer chain acts as a series of length, and so the fully stretched length means in this case one in which all the links are laid out in a line. Of course, one can go to an extension that is greater than 1 in terms of this fully stretched length by stretching the individual links themselves. Now, why do you get a force at all below the fully extended length of the molecule? Well, DNA is a polymer, and I recommend you to do the exercise on the entropic elasticity of DNA in Chapter 3. And so, associated even with double helical DNA, which is quite stiff, there is a persistence length, which is, roughly speaking, the length over which the polymer changes its direction by a significant amount. So over this length, you can replace the model of DNA by a freely jointed chain, where, let's call this the persistence length. One has units of lengths equal to the persistence length, which are then freely jointed to another unit of length LP, and these things add together to form a drunkard's walk. So in equilibrium then, the end-to-end distance is actually 0. So you have to apply a force to extend the DNA at all. Now, an interesting and not obvious thing is that larger forces are generated by stretching single-stranded DNA than by stretching double-stranded DNA. But this is because single-stranded DNA has a much smaller persistence length. For double-stranded DNA, it's about 50 nanometers. For single-stranded DNA, it's on the order of 1 nanometer. And therefore, single-stranded DNA has much more entropy to give up when you stretch it by a given fractional amount. Double-stranded DNA therefore generates a fairly low force, until you start to extend it to its maximum length, and then the force shoots up. And then a very interesting thing happens. It now yields to form a new structure that is still the subject of some debate, and eventually the two curves join. So a great deal has been learnt about the mechanics of DNA from experiments of this sort. Let me show you in the last slide, as promised, the use of a magnetic bead to pull on a molecule. Now, magnetic beads are not actually traps in the sense there is no equilibrium position for the bead. These are superparamagnetic beads, and we'll talk about superparamagnets a bit in Chapter 9. But in the presence of a magnetic field, they generate a dipole moment M. It's quite easy to show that a dipole in a uniform field experiences no force, but in a field that has a strong gradient like this, the magnetic moment does lead to a force proportional to the product of the induced moment in the bead and the field gradient. So what this means then is that if you have a bead tethered to a surface and you arrange the magnetic field gradient so that there is a force away from the surface, one can pull the bead away from the surface and exert a force on the molecule tethering the bead to the surface. It turns out that one can measure displacements of the bead to really even the nanometer level by simply looking at how the optical diffraction pattern around the bead changes as the height of the bead changes. So one can measure the height quite accurately just with optical measurements. And so one can generate force distance curves for single molecules then by simply applying magnetic field gradients of various strengths and seeing what the equilibrium height of the bead is. But you can do more than this. It turns out these beads are never uniform. They're sometimes more easily magnetized on one side than another. And the result is that if you rotate the magnetic field, you can put a torque on the bead and you can wind it up. So what this slide shows is DNA that was originally pretty fully stretched, and the bead was then rotated in a field in such a direction as to overwind the DNA. So now the double helix is being wound more tightly than it should be. And what you see is a very interesting instability in the system. When you overwind the DNA to a certain point, it becomes energetically favorable to form a little loop out the side of the structure. These are called plectinemes, and while you've probably never seen a plectineme in a DNA molecule, you will have seen them in those very long telephone cords, sometimes used in kitchen telephones.